Hello, this is an overview of a HDA. Super quick. The idea being you want to fill a crate or a box with points, or you use those points to instance geometry on them, but you want them to be equidistant apart and not exceed the bound. So it's quite similar to points of volume, which is a kind of what I'll go through quickly, and I'll talk about how some of the usage might be more applicable with HDA because you get a bit more control, but points per volume does get the job done to an extent. So the main thing is it spawns points on the edges, and again, if you're using just for general, that might work, but if you're trying to fill something up and your points are here, when you either apply p-scale or you put your instance geometry on it, it's going to poke out, and we don't want that. So you kind of have two options. You can just blast them when they're on the edge, or you can obviously reduce the point separation, and that will drag them closer. You do need to take into consideration p-scale. I think by default it's 2, but we need to be 0.5 because it's obviously radius, and that is one way of obviously doing it. You can fill something nicely and cleanly, but it's kind of like you have to dial it in yourself. So the idea of this internal points HDA is you can also do this, but you can specify the radius of the point, and it will basically work out, okay, take the axis length of your bound and how many of these points with this radius can I fit into it, and it'll try and source them. So if I demonstrate that now by just reducing this value, you can see it adjusts like that, and it doesn't exceed, and it's always packed together, or with an equidistant spacing between them. So one of the options, if I just increase this a little bit to something like this, is there's the spacing that's equal. We do have the option to center the points, which are basically pack them together centrally within the bound of the object. So this is why you'll get your gaps, and that's a lot more similar to, if I just show this, with the blast by bound, with if you were doing points per volume. So you can still achieve that effect with that, or if you want to just kind of have it, you know, nicely scattered evenly, we can just turn center points off. So there's one way of doing it. You can do by radius, which can be quite handy if you know the incoming size of an object you want to fit into this. So there's one method, and then the other method is by count. So you can either do by equal axis, and this is basically how many points it's aiming to source per axis of the bound of the object. Now, I keep saying the bound because it's based on the bound. It was originally made for filling a crate up, which is a box. So I'll talk about why that might be a bit limiting with more bespoke topology in a sec, but for the sake of it, this is how it's working. It's doing the X, Y, Z axis. How many of these things can I fit within that bound? So equal is obviously self-explanatory. It's trying to fit the same amount per axis. And then you can also specify, okay, a per axis amount. So this is useful if you're trying to fill up a container, for example, and you want it to be packed fully on one axis, but you only want it to be too high. Or, there's various use cases for this, but you have a bit more controllability here compared to the points per volume, where obviously it's uniform. So that's the main sort of advantage of this method. I'm going to switch back to radius just because it's a bit cleaner. So next is the output attributes. We can output p-scale, scale, and ID. If I show that right now, you can see all those values. Scale is really if you're using the by count method and you're having different per axis, because I'll show you in a sec when you instance geometry. If you, for example, want to put boxes or cuboids, you can use the scale attribute to stretch them accordingly. So if there's more on one axis than there's another, it won't just be a box, it'll actually, like a brick, for example. But for the most part, p-scale should be fine. An ID attribute is obviously an individual ID per point it creates. And the other two options are you can remove the outside. So this is what I'm talking about with bounds. If you have something that has slightly less cubic geometry, i.e. a sphere, it still is using the bound of the sphere to source the points. So if I just go back to radius for a second, and let's drop it a little bit. You can see it's still a little bit cubic, but that's because it's using the bound of the sphere. So remove outside basically shows you where it's spawning, which might not be the most efficient, but again, it was built for kind of filling boxes up. But if you wanted to put any kind of geometry in, just make sure remove outside's on, and it will make sure it doesn't exceed those bounds still. And then keep original geometry, just keeps the same incoming geometry. So I don't know if you wanted to do like a vellum sim or something strange with something with the shell on still, then that would be an option. So that's just built in there. And then again, just to touch on the kind of bespoke topology stuff, if I take something a bit more high res and odd, like the rubber toy, you can see that, okay, we can still scatter points, but it's limited because it's using it of the bound. It's kind of has to find the right seed for that, which it can be done. You just have to go high res. It wasn't built for this, but it's there if you would like to do that. Still like that. There we go. And both methods work, and you can still center them, but for the sake of general usage, it's probably best to just stick with a box or a cuboid like this. So I'm just going to run through a couple of examples of what you can actually use these points for. The first is fracturing. So if you want to cut your geometry up into perfect even sizes, this would be a way of doing that. If I take my box and I input my points as my Voronoi points, you can see that it separates them all into nice, even, clean cubes. If I enable center points, it would obviously change that because it's trying to draw the points inwards. But by maintaining that equidistant space, you can achieve this effect. Another example is if I'm just going to reduce this slightly, you could actually save yourself a little bit of time. You can jitter these points and you can get these kind of traditional Voronoi shapes, which previously you would obviously have to do an ISO offset, scatter the points into that, and then use those as your input points. You can kind of, it's an option to use this HDA with point jitter on the end. Again, not what it was made for, but it does work to do that. So another example is that we can copy geometry onto these points. So if we copy, let me center them for this example. We can copy cubes or boxes, and just to show that they are actually there, that's what it does. And this is obviously using the p-scale attribute. So if I disable that, it breaks. Or if I enable the scale, that's still fine because it's cubic. But if I put in a box, it actually, you can see it makes them like bricks instead, because it's the scale uses per axis as opposed to a uniform scale, which is what p-scale is. So if you want to make a pallet of bricks or a wall of bricks, you could use this. I'm going to go back and just use boxes for now. And you can also obviously replace that with different geometry. Spheres would do the same. If we do the, I don't know, a rubber toy, whack him in. There he is, perfectly even. And again, because it's using that radius, it's nice and safe. And why not, if you want to destroy something with a bunch of cubes, maybe you could use this to make like a Jenga tower. Who knows? But those are just a couple of examples that you can kind of go with it. It's mainly about just filling up your bound with objects or points. So hopefully that's useful. And let me know what you think.